Close to it, yeah.
This is what get.
Yeah. Well, you offered, yeah, you offered bonus points, right?
Yeah, I have to This is last week of classes, so we have one more to go. The final one will be even more. See, I could bet you for this. We have you know Michael, right? You know Michael? Michael, Vince, Sam, right? So these guys have done senior design project on this awesome board plate. If any class can related to this project is this class. A lot of same stuff goes in the what you have done. So I think this senior design project will be, if you are looking later on in what, 5th year? Yeah. If you want to do something like this, then get in touch with me, or I think most of you, these guys will be working, they will not reply. Right? So yeah, all over to you guys.
Morning, guys. All right, so for our senior design, we did a autonomous quad plane. Just the background, kind of, you get two big classes of UAVs. You have like your fixed wings, like your remote control airplanes or your drones, like big military drones, or you have like quadcopters or hexacopters, like stuff with like just forward-facing propellers. We kind of slammed them together into one big system here, so it's got the best of both worlds. And so the objective is to take off like a quadcopter and be able to maneuver like a quadcopter at low speeds, and then have the efficiency of fixed wing flight. So you're not running the propellers at full go the whole time. You're just using them for takeoff and landing. So you guys have already got a taste of it, and you're going to get a lot more of a taste of it over the course of 5 years. You're going to learn a lot. And so the goal of this project was kind of just to slam everything together, try to use as much of it as we could, and move as fast as possible. So like we didn't spend a lot of time doing the system stuff. We were pretty much just iterate, go, had an idea, try it. So that was a pretty cool way to approach this project. You can see we got a big list of skills that some of us had before we came in, others didn't. Pretty much everyone got a taste of everything, which is pretty cool. So timeline, we made this decision about almost a year ago at this point, where we were going to do our own senior design. So when you get to your 5th year, you're going to be faced with a choice like UAV design, design, build, fly, like the Aerocats team, supersonic transport, like the Sonicats, and then what's the last one? Space design. So we like those. Like we didn't have anything against them, but we kind of wanted the flexibility to do our own thing. And we like Dr. Sharma a lot, so it was really easy to find an advisor to support us in that regard. So initial decision was made May last year. We started a parts list pretty soon after. I think we had parts almost ordered right when we started school, which was nice. Had a few months of the autopilot testing and tuning, so you've had a taste of that now, where you got all these gains and you got to get them right. So that took a little bit. But eventually we got flying like just an airplane pretty well. Then we put the quad motors on it, and then we went to go make it fly like a quad. It flew pretty well there. Our final design was probably done somewhere between November and January. It's kind of a final design. It's kind of a loose word, because we came up with something and then we just kept improving upon it throughout the course of the rest of the year. So the first manual flight actually of it taking off vertically and then transitioning was just last month, actually, or early this month. And that was a big deal for us, because we'd always struggled with the transition between the two flight regimes. Requirements. Had a few big ones we wanted to really knock off. Obviously, we want to take off and land in a VTOL configuration, so take off, land. That's the whole quad plane deal. Wanted to hit the autonomy stuff pretty hard. We did some path planning work that we're going to talk about later. That was pretty neat as well. And that's like we were going to hit each waypoint within 50 meters. And then our big objective that we haven't quite hit yet, we haven't had a good flight to do it yet, is we want to triple the time of just a regular quadcopter flight. So this exact model will fly around 5 minutes, just sitting there at a hover. So we want to be able to have it float up there for a total of 15 minutes. So increase the efficiency by 3 times. System overview. We're going to get in the nitty gritty of this as we keep going. But so for the flight controller, we use a Propellor 2. This is a commercial off-the-shelf flight controller. Pretty much anyone hobby grade is doing autopilot stuff is pretty much using a Pickstock. We ran autopilot on it. Another pretty common software. And then the sensors, which is pretty fun. So the pitot tube down there, I don't know if you guys can see it on the actual airplane. Yeah, the whole little airspeed's different than ground speed deal. Like that's a big one. It actually does matter. IMU, so all of our patrol yaw stuff. The optical flow is really neat. That's like almost like a 1D LiDAR that goes down to the ground and helps us stay nice and level and hold a spot. And then the barometer, so a good idea of altitude. And then you can see on the actual view. So it was a regular airplane. We added the 4 quad motors. You see all the frame for that stuff. Through a lot of electronics and cameras, and then our retractable landing gear, which are pretty cool.
We started off early in the process, just like a conceptual design phase. So this was the very early months of the project. This was like August now, maybe before that. And some of the big overarching design decisions are making. So first of all, what airframe, what we're going to use. So we did some research on different airframes. There's these types of airframes, technically a big lighter. We're going to have like more robust tank-looking planes, push planes in the RC market. So figuring out what airframe we wanted to use for adding sensors, adding the quad motors, doing all those types of things, as well as like what the power margin requirements are to sufficiently lift the device, both in straight level flight and then hovering capabilities, and the sensors. So we talked about all the sensors that we have on board, and really early on in the process, making sure we knew what we needed, what those were going to cost, where they could go on the airplane. That way, the airframe that we got would be able to match to all those different sensors. And then all the final stage the company software, so the Pickstock and the autopilot plane software, so we could actually run the airplane how it's supposed to run. And communication. So we have an RC controller that we can fly in manual mode. Then we also have a video transmitter on the bottom of the plane with a little camera. So Jen's our famous pilot back here could wear his little goggles and fly and recover if it got into some bad situations. Early on, we made the weight tracking sheet, which you can kind of see up there on the slide. This was to track all of our estimated weights for different parts to make sure that we would be able to, like I said, provide sufficient lift and thrust from all the different motors. It turns out this was like done in August, and our final airplane was like pretty much spot on what we estimated it was going to be. And this was like we added like a 20% buffer for water and some other stuff. So our initial estimates were really good. It enabled us to have sufficient power later on in the design process. But then as far as like part design, so as Vince said, we got like the initial airframe, which you can kind of tell what it is. It's like the main white wings and the white airframe. The red control surfaces were enlarged, which I think we'll talk about later, and some testing and analysis. But everything else on the airplane was basically designed. So we started with some motor mounts. So we had the motors, we got the motors in. We designed 4 motor mounts. You can see on screen, but then in real life they are here. So we figured out how we wanted to clamp them on to make sure they work in the. We also designed boom holders, which so basically there's a metal bracket inside the wing, which is underneath these 2 things on each side. So that way these can screw directly into that. And these are detachable. So early on in the testing phase, we didn't want to fly with like just the booms. So what we did is go to Tractor Supply, what engineers do, and we bought big bolts and attached bolts to the airplane and flew it right into a tree.
Right into it. Flew around first.
We also have these support rods. So early on during testing, some of that stuff was obviously done in integrations. So during some initial testing, we found that it was with the quad motors is twisting a lot. So like both wings would deform quite a bit. So we added this support rod holder. So those are on the 2 motor mounts. They epoxied the motor mounts. And like in hindsight now that we have finalized design, we prep one piece for all this stuff. And then we also have the support rod mount for the actual connection to the vertical tail. And then Michael's famous invention was the landing gear. So you can set the landing gear to come down whenever you want. You can do it manually from the RC controller. You can flip the switch, it'll go up and down via these 4 servos. You can also program it into the autopilot software such that if you reach a certain altitude and you're in hovering mode, the landing gear will come down. Just cushions will fall a little bit better. That way, you know, there are some critical centers and stuff on the airframe, and their optical flow here, some other things. So that just prevents it from hitting. And also, this is not part of the airplane. This is just something that happened to a tripod from EXO last week. There's also the Peter prep holder on the front. This was V2. The V1 iteration wasn't quite as pretty. It was basically just this little hole that we stuck the thing out of. And then the optical flow sensor holder. And then the last part is these wire loop bearings. So when we flew for the first time, underneath there, there's a lot of wires for all the different servos, the control surfaces, all that stuff. It was kind of hideous. We had it like taped up, and then we're like, okay, we should design a fairing. We also tried to get back some of the lift that we were losing from all the different wires hanging out there, increasing the drag. So we made this aerodynamic fairing that increases the the wing forward a little bit in this location, and also covers up all the wires. Those are some of the main designs that we did. A lot of this stuff didn't happen right at the beginning. Some of the main stuff did, like obviously the motor mounts, the rod holders, and boom supports and all that sort of stuff. But then some of the stuff was iterated on throughout the process as we learned different things through testing. Then as far as manufacturing goes, so as you can kind of deduce based on what I just said, most of the stuff is 3D printed. So everything basically on the airplane was 3D printed with tough PLA filament. However, there's the 2 metal plates inside the machine, or inside the wings, was routed on a CNC router. We routed an ISO grid pattern to reduce the weight, which I think we'll see in a little bit as well. And lastly, the only other kind of manufacturing method, if you want to call it that, is these wing fairings. We actually printed like the outer perimeter of it, like just a few layers of filament on a 3D printer, and then we used expanding foam in a mold. So we put the outer perimeter inside the mold. That was like a big housing, and we put expanding foam in, so that way it would fill it all the way, make it a bigger structure, but more lightweight than just a hunk of plastic on the airplane. So those are kind of the 3 main manufacturing techniques that we use. 3D printing is awesome because you can just iterate, and we're also able to do some testing later on, like make sure all the parts were like weren't going to crack under certain loads, under fatigue, cycling the system on and off. And there's a lot of flexure when you turn the rotors on and back off, on and off. So we did some testing with that. We got some cracks initially, so we were able to 3D print parts in different orientations, different filament, different head field perimeters, all those different settings that you can explore in that field. And then after kind of some of the initial part testing, the initial design, conceptual design stage, and getting some stuff into our house, I would say our shop, where we use Michael's as our shop. we began to do some validation. So we wanted to validate everything that we could before we go fly. That way we weren't going to send it up in the air. We're just going to fall out of the sky and crash and call around to say, hey, can you get a new airplane tomorrow? So this is actually the only airplane we use. We had one before this, just to like test some initial sensors and stuff, but we never had to get a whole new airplane. It's pretty impressive. So we wanted to validate the quad motors as well. So there's some prop thrust, test stands, creation and testing for the props themselves. We also set up some of the initial sensors, make sure that they're working properly, blew into the P tube, is it reading what we think it's reading, all those sorts of basic activities. We did some basic CFD on the aircraft wing propeller as well. So you could kind of cross-check the propeller and what we're cross stand to make sure that they're close to each other, they validate one another. And then we also had, like I said, an initial airframe that was a little bit different, just to understand how the software was working and utilize it a little bit as a flying test bed. So we flew that just as an airplane to understand our autopilot software, how to do waypoint mission, not just to sit in the air, probably stuff like that.
So I'm talking a little about validation, but there's a lot of like hardware and stuff went along with this. So the first thing we made was our thrust test band. Again, in real life, when you want to take off for the first time, you want to make sure it takes off and you don't just sit there and make a bunch of noise. So we created a thrust stand just to ensure that we had enough thrust from our 4 quad motors. So picture on the right there is basically like a chunk of 2x4s and then a load cell and some microcontrollers, basically like an Arduino, but I think it was ESP32. No. Okay, but yeah, so basically just recorded the data for each PWM signal that we were sending it. So the plot, you can see that we're stepping up PWM. So on the right side, there's like your actual signal. Most RC PSCs and servos go between like 1100 and 1900 or 1000 and 2000. So we just wanted to make sure we knew what range corresponded to what amount of thrust and that we were going to have enough thrust in the end. So we got about 3.5 pounds of thrust from each motor using a 4-cell battery, which is like 14.8 volts nominally, I guess. And then, so, 3.5 times 4 is 14. So we have 14 pounds of thrust at peak, highest throttle possible, and our plane weighs about 7 pounds from our weight sheet. So we knew we would be able to take off with plenty of thrust margin and be able to hover with enough control.
We also use the same thrust stand for we put on like the whole boom, so we put like one arm on, and like that's how we figured out that when you cycle it on and off 20 times, one of these parts might blow up and just damage your airplane. So we reinforced and we retested, and that's how we figured out that we should probably put some different settings, some tougher filament, that sort of stuff.
Yeah, like essentially the first parts we had actually cracked when we as the test was done, we went up and touched it, and like fell off the thing because it was just cracked. Okay, that's not good. Because one of these motors gets loose while it's spinning, it's a real problem. So and then also we tested the carbon rod, because the carbon rods, although they feel really stiff, actually have some deflection when there's 2 motors pulling up on them. So we just kind of stress tested them and made sure it wouldn't fail.
Stress testing of the carbon rods because we drill 2 holes in them.
Yeah.
Basically the full diameter, like the carbon rod has a hole in it on the one side. Now we can fish some wires through and make it a little bit prettier. So we were a little concerned about that. 2 holes in it, put it close to each other at the middle of it. So we, did our best to make sure it wasn't going to snap.
Mm-hmm. And then we did some CFD as well. The prop CFD was just kind of auxiliary to our thrust stand testing. Obviously, the thrust stand is going to be more accurate than CFD most of the times, but we kind of just wanted to do it because it looks cool. And then we also did a wing CFD because we weren't sure if this airframe would be able to actually lift with we almost doubled the weight, or maybe a little bit more, with all the extra stuff we put on there. So we're able to create about 5.5 pounds of lift per wing, so about 11 pounds total for the whole plane, which again is above our 7-8 pounds from our weight sheet. So we knew we were good there. And then that was also, I was talking about the bolts. That's how we validated the CFDs. We put bolts on them that were roughly equivalent to the weight of one of these booms. And then we just tried to fly, and it did fly, but not well, but that's all right. And then for the CFD, we use ANSYS CFX, mostly because that's what I was familiar with. But it's a great tool. I know they teach Star CCM here, but I think right now, right? Yeah. Yeah. Yeah, I think CFX is a little more intuitive than all the ANSYS tools are more intuitive than CCM, but they both do the trick. So whatever floats your boat. Yeah, so I mean, it's not necessarily necessary, but it just gave us reassurance that when we turned off these quad props, and we tried to transition, it's not going to just fall out of the sky. That'd be bad. No. And then also we did some FEM. This is just in Nastran. So we had these aluminum plates that we machined. Like I said, they're up inside the wings, epoxied in. And we just wanted to make sure that since we removed over half the material on the plate, that we didn't just destroy the rigidity and structural ability of it. Obviously, it's an aluminum plate and a foam wing, so it's not. The foam is probably more of a concern than the aluminum is, but it's still cool. We learned a lot, and we just validated that we've got plenty of safety margin on all the axes of twisting. And so for your ground control system, there's like 2 programs that go with ArduPilot. Mission Planner, which is what's shown here, and then Q Ground Control. We kind of bounce between the 2 because they each have different functionality. But this is like a really good interface that you can basically, plan out missions that you want your plane to go on. You can command it to do things. You can switch flight modes, adjust your parameters live. So it can be in the air flying. And if it's oscillating, you can say, all right, dial up the D gain on our roll axis, and it will like immediately upload, change it, and then like smooth out flying. So it's really incredible. You can do that without having to like land and change things, and plug it in, whatever. Yeah, for your games, that'd be cool. Yeah, for sure. And then the radio we use, I think actually. They're at 900 megahertz. They broadcast and receive at 900 megahertz, and they have like a range of like 10 kilometers. So we could, in theory, fly that far, I guess. Not sure the plane would make it that far.
Our
but
pilot doesn't like to. It's pretty fast.
Yeah, and obviously you gotta be careful when we think we know what's going to happen with the plane when we press go, but you never really know. So yeah, this is the one we forgot that one time. Yeah. Okay, and then and then with this, there's like 2 ways you can plan out your path, right? You can just draw waypoints, and then tell it to go. You set altitudes, speeds, what flight mode it should be at, things like that. We wanted to do or kind of explore some like cooler options, I guess. So we did explore some of the traditional path planning techniques like RRT, RRT star, A star. If you've ever heard of those. Those are like optimal path planning, so you can get around obstacles, things like that. But we realized like there's not a ton of obstacles in the middle of Indiana in the air. So for the time being, we were like, let's not worry about obstacles and just do like straight line path, because that's obviously the fastest. And then let's try to smooth that out a little bit. So what we came up with was, you see the red line is just like a series of waypoints. And then we smooth it out with just a moving average filter, like the most basic filter you can put on things. And then you can see that actually takes you in your corners actually shrink. So you never actually hit those waypoints. So I measured the distances between those, actually automated, and then it like shifts those back out until you get the path on the bottom. And you get this nice smooth path that goes through all of your waypoints, but also tries to stay on the straight line distance and just get there as efficiently as possible. And then this actually exports as a waypoint file, which Mission Planner can read. So if your path there on the left, you export it as basically a tab delimited file, and you can then import it. You have your path already drawn up and smoothed out the way you want. So flight testing, there's some pictures here. The pictures of top two are when it was hovering. And then the bottom left is fixed wing flight. And the one on the right is just, it hanging out on the ground. Then I have a video that I can show here. So I'll try to talk over this a little bit. Wait, oh. Hold on. Let's see here. No. Oh, we'll get it. We'll get it. There it is. Got it. All right. So this is talking a little bit about the flight modes earlier. So this is it. Manually hovering. So this is Vince flying, and he's controlling basically your phi and your theta values. So modulating pitch and roll. And then it tries to, make sure he's not doing anything crazy and kind of make sure it doesn't crash. And then the psi value is kind of uncontrolled unless Vince issues a command to y'all. And then that's when we put it into basically a loitering mode, which means it just tries to hold its position. So your altitude and your two latitude and longitude points, and then also phi theta psi, all of that. So it's basically just sitting there. I think in loitering mode, you can tell it to go up and down and kind of nudge it. Right. So just hanging out. And we were kind of shocked initially that it has, well, not shocked, but should have seen it coming, I guess. But when you have a quad with wings on it, the wings cause a lot of disturbances whenever there's moving air. And then, obviously around the props, there's a lot of moving air. So, yeah, if there's like a little tiny breeze, you'll see it like kind of move in the wind and things that normal quads don't have issues with. And there's a landing gear going up and down.
The things that we overlooked, we shouldn't have overlooked.
The first couple times are pretty,
yeah. Do some weird spins.
Yeah, initially the yaw control was pretty bad. And most of that, I think, was due to just all the extra stuff catching the breeze. So we didn't really talk about this, but the motor holders are actually like canted in 3 degrees. So some component of your thrust is actually going outwards. So when you when you like change the thrust of each motor, you're actually providing like lateral forces too, which gives it way more yaw control, and that smooths things out.
I could be wrong. I think the first time we tried to take it off the ground, we wanted it to be as controlled environment as possible. And we're kind of idiots. We were like, let's do it in our bedroom. And it's kind of you're like turn everything off. You're like standing behind the door,
I just wanted to see if it could like go up and then down. And
maybe we should go to the house.
Yeah.
At that point, we were like, that's there. And then some of the what's that happening?
Yeah, it kicks up a lot of result.
So we didn't work out when there's a lot of cross around. We learned our lesson.
Yeah.
And anytime like looking at people's, it's like really hard to understand like what someone else is on that line. So you would do things that you would just be sitting there and have no idea.
Yeah, the other frustrating thing is like we could make changes to it because it's all open source, but there's like a software in the loop simulation you can do with their autopilot, which is very handy. But the version we were using, since we were doing on Windows, was like a pre-compiled version of the code. So to make changes, we'd either have to go through all the work of doing all that, which would probably be a nightmare, or we'd have to just like change it and then upload it and fly it, which probably wouldn't go very well. So yeah, so there's limited changes we can make besides the like 3 million parameters you had to tune, which was obviously inevitably enough to get it to fly. But yeah, so this is like a manual quad plane flight. So Vince is still somewhat in control, but the plane actually takes care of most of the transition for you. It holds its altitude. It makes sure it stays within certain bank angles. It's kind of like,
It's like assisted flight.
yeah, essentially. If you've ever used any autopilot stuff, it's essentially in fly-by-wire A mode while it's flying. And then once you like tell it to transition, it takes over most of the stuff besides the back throttle control. And then it gives you authority when it determines. So. Which we also figured out why this was.
Disconnected.
I think I realized like 2 days ago. I was like, oh. Yeah.
Let's kick it on the back.
So now it's flying like mid transition. Let's say right there. It's transition to horizontal flight. Yes, it's kind of hard to see.
It's the max altitude you guys have flown at.
399.
No, I think we got up to about 100 feet. Yeah. I think it was about 100 feet. When you climb vertically, you're like waste a ton of power. So you want to get to horizontal flight mode as soon as possible. Let's see. Transition back to vertical flight.
Which sensor did you end up detaching?
So on the bottom, there's an optical flow sensor, which actually you'd think would give you like position hold, but it actually outputs your PQR, your like angular velocities. So I should. So we meant to detach the airspeed sensor because when like wind gusts happen and stuff, it can put a ton of noise into that sensor. So we wanted to try with just GPS ground speed, using that as your airspeed essentially. And autopilot actually does like some calculations to calculate airspeed from ground speed. So we wanted to try that, but I meant to unplug the pitot probe, which I thought was in the CAN bus slot, but turns out the CAN bus slot was the optical flow sensor. And the optical flow sensor was where we we're getting our main PQR values. So that's why it was like kind of dancing on climbing. So it was basically not trusting. It didn't have any values, so it's just like reverting back to IMU stuff. But then it probably wasn't going through the full like EKF calibration or calculation and everything. So this was our first autonomous takeoff and landing. That's at a park kind of right up the street. But this is just like going up, does kick on the back prop, and then goes and then lands. So it doesn't fully transition, but it shows that it can, navigate between GPS points. And then this is like all autonomously, so there's no control, it's just you press go and it does that. And then this is like a full autonomous quad plane flight. This one ended, at the end of this, we had to kind of take over because, I'll talk about next slide, it didn't have a ton of roll control as a plane. So that's the reason we extended the control surfaces.
Do you just completely turn off the propeller or the 4 vertical propeller thing?
Yeah, once it's fully transitioned, they're off.
Did you have to register it for the FAA?
So not. It's essentially just an RC plane, so. Yeah. This is a hobby endeavor.
Also, they were flying on the first one.
Yeah. Yeah, we didn't fly over top of anyone and things like that. No, out there. All right, we knew that. I don't know. What time is this class end?
15.
Yep,
Oh.
this is your exam.
Okay.
So we then let me know what game they should do.
Yeah.
We don't know.
Yeah, she's.
You think like simulation modeling hard and soft like Python, mine is like 10 times.
Yeah.
All the other.
We had one flight where like the flight that should have been a perfect autonomous flight, we got up and our GPS signal went from like 12 satellites to 5, and it reads out what the accuracy it thinks it is. Like normally it's like sub 1 meter, and it went to 300 meters, and so it was just like I don't know where I am, and that like destroyed the flight. Like that's when I started like hovering over that house, and we're like, okay, this isn't good. So so things like that happen when you're doing hardware. Hardware messes up all the time. So a little bit different than software. And there's a crash video too. This is where we broke 2 props. It was supposed to just do the same thing as we showed last time, where it just translates, but then it decided to go into the wall. So that's where a couple of the nicks in the wings came from. And then, so data analysis was pretty key. You guys all have plots in your autopilot, or you should. So we pulled that data afterwards and kind of looked at it. So this map over here is actually the autonomous quad plane flight that I showed. And you can see in the top 2 graphs is your pitch and commanded pitch and roll and commanded roll. So the green is your actual roll and your actual pitch. So you can see that's kind of outside of where it was supposed to be based on what was commanded. And if you look at the actual RC signals, you can see like it was at full deflection, but just nothing was happening. So we determined from this that we need to enlarge our control surfaces and also increase our deflection amount. So that's what we ended up doing. So now control surfaces like very exaggerated. So if it was just a plane, it'd probably fly horribly. But when you got all this extra mass, higher moment of inertia, it definitely flies a lot better and controls itself very well.
Basically increasing the CM.
Yeah. Right. Mm-hmm. It's essentially increasing like the moment you can apply from your control surfaces.
Basically, all the modifications you see on the airplane that weren't like basically on a final design picture, but we went from a final design and this looks a whole lot different. And that's some stuff we found during all stuff we had found during flight test. The big thing that saved this airframe a whole lot was the ability to slam it back into the Q loiter mode. So like no matter what altitude we were at, it was really easy to just like flip the switch and have the thing just right itself and hold the hold whatever position it was at.
There was one time where it hit falling out of the sky, and Vince was able to stick it back into quad mode and it just immediately picked itself back up.
Mm-hmm. And then one thing that I had personally that we're going to recommend for Dr. Sharma to buy for next year's team is a pair of like flight goggles. So that just gives you a really good. They knocked me for it because I would see something going wrong and I'd take over, and these knuckleheads would be sitting there 300 feet away. Oh, it was fine. It wasn't fine. So the goggles are really nice to be able to see, like, even if it's far away or up high, like you know exactly what's going on, and you can fly it that way. That helped a lot. We saved quite a few. We had quite a few crashes, but we saved a lot of like catastrophic like airframe ending crashes because of that. That's about it for our big flight test findings.
We're gonna do this. We did a lot of variations and testing, which is great. But early on in the process, we kind of like doing at the wall, threw stuff at the wall, felt stuck, and like various at the time, but doesn't everything we learned in the first year. And sure enough, I just made a teacher follow this something. Once you start like figuring out maybe one variable at a time, you can really isolate the problem and then find solutions for your issues that way. So you can see it doesn't seem like you're saving time when you think one variable and more data analysis and all that sort of stuff. But it's really carried because instead of just like looking at data and saying like, okay, change these two things, which one of these actually impacted it? You know for a fact that this change made an impact on our system. Well, and then like I didn't know with that, create a practical test sequence. You know, like, like put those two together and fly autonomous. Do that essentially. Out of someone's hand and go do the phone. So create a practice. And validate the science. Simulation. So I think we're going to through the front end testing. But on the first end, whole being something frequently we had an issue where this is my fault. This is my fault. And instead of degrees, so we're like degrees.
It's been a flight where Vince is actually flying and he tried to do full roll and just nothing happened. And we're like, okay, so that's not right. And then went back afterwards and our like max bank angle was 30 centigrades instead of 30 degrees. We're like, okay, duh. Makes sense now, I guess. But I'd never heard of centigrades, but it's a thing. Watch out for it. Yeah.
It has to. Like, these things are
and I think that's even like I don't know.
Yeah. So, it's like the wherever the
there's one big issue. Working on it. Those things matter. And it's kind of honestly, I think at the beginning of the project, we knew it would require a lot of work, a lot of different coordination between areas. But at the end of the day, we found it. Would it be simple? Would it be relatively simple? And seemingly simple projects in engineering in the aerospace world require a whole lot of knowledge and coordination between many different functional areas. Now, one of our beginning slides, we saw all the different things that we touched that are part of our aerospace curriculum. And senior design, this project is able to pull all of it together, touch a lot of different areas. So it's been a very great, line. And I think that we're all happy with the work we put in to get to the point that we have and showcase what we learned for 5 years and have a cool project and product out of it.
All right, any questions? Yes, sir.
How do you account for wind?
You mean like while it's flying,
Yeah.
or so? I mean, just like any other airplane, it tries to battle it as hard as it can. So one of the interesting thing that we found somewhat by accident is that when it's taking off, obviously you want to take off into the wind, right? As a normal plane. So when it's taking off autonomously, it does what's called a weather vaning. So it takes off and then lets the actual tail and just like the like